Welcome to the Deep Dive. Today, we're tackling something really mind-bending. It's about the James Webb Space Telescope and some findings that are, well, pretty unexpected.
Absolutely. And it's not just small details. We're talking about discoveries that could potentially shake up how we fundamentally see the universe.
Right, because we all learn that telescopes are like time machines, don't we?
Yeah, that's the standard idea. Light from distant stars, distant galaxies takes billions of years to get here. So when we look far away, we're looking back in time. Simple enough conceptually.
Peer further, see earlier. Makes perfect sense because, light travels at a certain speed. It's not instant.
Exactly. That's been a cornerstone of cosmology for ages.
Yeah.
But then comes JWST, the most powerful telescope we've ever built.
Okay.
And the data it sent back, it wasn't quite lining up with those expectations.
Yeah, that's the core of it. And instead of seeing galaxies that look much, much younger or less formed than what Hubble saw, JWST often just shows us the same galaxies, just, way clearer.
Sharper images, more detail. But structurally, often looking remarkably similar.
And that throws a wrench into the works, doesn't it? It really challenges that whole look-back time concept we thought we understood.
It really does. And this is where a pretty radical idea called motion theory comes into the picture.
Motion theory, okay.
It basically suggests that maybe this whole look-back time thing, maybe it's kind of an illusion.
An illusion. Wow. Okay, let's definitely dig into that. So the idea is we aren't actually seeing ancient history playing out billions of light years away.
That's the proposal, yeah.
So for this deep dive, we want to unpack that contradiction, what we expected versus what JWST is actually showing us.
And then explore how motion theory tries to make sense of this puzzle.
Exactly. We're aiming this for listeners who like getting into complex ideas, but without getting lost in jargon, and who appreciate those aha moments when things click.
Right. So let's start with those expectations. Before JWST launched, scientists had a pretty clear picture of what they thought they'd find in the really early universe.
Based on that fixed speed of light principle?
Correct. The thinking was JWST would peel back the layers and show us galaxies just starting out.
Like cosmic toddlers, maybe? Small, messy, not very organized yet. Maybe just beginning to form stars and clusters.
Precisely. Clumpy, chaotic, maybe. Definitely not grand, structured spirals like we see closer to home. The further back we looked, the more primitive things should appear.
But that's not what happened.
No. JWST started spotting these massive galaxies with surprisingly well-defined spiral arms, stars that look pretty mature, even significant black holes. All in regions of space corresponding to the supposedly very early universe.
It's like finding, a fully built skyscraper when you were expecting to see the foundation being poured. They just seemed too finished, too grown up for their alleged age.
That's a great analogy. And like you mentioned, the really baffling part is often finding the exact same objects Hubble had already seen.
Just clearer.
Way clearer. JWST's resolution is incredible, but the underlying structure often strikingly consistent between the Hubble view and the JWST view. Just sharper?
Okay, so here's the logical problem, right? If we are seeing light that's traveled for billions of years, shouldn't a much better telescope, one that can catch even fainter light from that same object light that must have left even earlier, show us an earlier version of that object?
That's exactly the expectation based on the standard model. It creates a sort of logical inconsistency with the data.
Right. If the light's been traveling that long, a more sensitive detector should pick up photons that started their journey sooner.
Meaning we should see the galaxy as it was slightly further back in time, a younger version.
Yeah.
Less developed.
But we don't, or at least not consistently in the way we'd expect. Instead of seeing a younger galaxy snap into focus,
We see the same basic structure, just with more detail, finer points resolved.
and this lack of, what did you call it? Temporal regression.
Temporal regression, yes. The lack of seeing things consistently wind backward in developmental time when we use a more powerful instrument.
That's the core observation that really puts pressure on the traditional look-back time idea.
It is. And this is precisely where motion theory offers a completely different explanation. It starts by fundamentally questioning what light is.
Okay.
Motion theory essentially says light isn't a thing that travels. Not a particle, not a wave, moving through empty space from point A to point B.
Whoa. Okay, hold on. If light doesn't travel, then what is it? How do we see anything?
Motion theory defines light as structured motion. Think of it like rhythmic patterns, compression patterns within the fundamental motion that makes up the universe.
Rhythmic patterns in motion itself.
Exactly. These patterns don't travel from the source to us. They shape the motion field around them, and that shaping propagates.
So it's less like a messenger carrying a note across a vast distance and more like a ripple spreading outwards, continuously reforming the medium.
That's a good way to think about it. It's about the structure of motion itself being patterned. And this changes everything about detection.
How so?
In motion theory, detecting light isn't about catching an ancient photon that finally arrived after a long journey. Detection is a local resolution event.
Local resolution.
It's described as a real-time compatibility event between motion systems. Basically, your detector, like JWST, resonates with or resolves a pattern of motion that is currently active in the universe.
Ah, okay. So when JWST sees the same galaxy Hubble saw but better.
It's not seeing older light from that galaxy. It's achieving a higher resolution tune-in to the motion pattern that still exists and represents that galaxy right now.
It's resolving a present structure with more fidelity, not looking deeper into its past.
Exactly. It's like getting a clearer radio signal, not picking up an older broadcast from the same station.
Okay, but wouldn't the standard model folks just say, look, it's the same light stream, JWST just has a better camera, so it sees more detail in that old light?
That's the natural counterargument, yes. Both telescopes are pointed at the same stream of incoming photons. One just collects and resolves them better.
Seems reasonable on the surface.
It does. But motion theory proponents argue that if photons were traveling billions of light years, a significantly more sensitive telescope should reveal distinct signs of that time difference. It should be able to pick up photons that left earlier.
And if it did pick up those earlier photons, what differences should we see?
Well, you'd expect potential changes in the galaxy's structure. It might look less organized, maybe slightly shifted.
Right, because galaxies evolve.
Exactly. You might see fewer mature stars, maybe a smaller central black hole, less defined arms. You'd expect to see an earlier evolutionary stage.
And maybe even tiny changes over time if we kept observing.
Okay.
As slightly different aged photons arrive.
Potentially, yes. Some kind of observable temporal drift or evolution, even on short timescales, wouldn't be out of the question if we're sampling light from different departure times.
But the key claim here is that these expected differences, they're just not consistently showing up in the JWST data.
That's the argument. Time and again, the observation is same galaxy, maybe slightly different viewing angle due to perspective, but fundamentally the same structure, just much, much clearer.
And that consistency, the lack of seeing younger versions, is what motion theory points to as the smoking gun.
Correct. They argue it's strong evidence that we're not detecting ancient traveling light, but resolving present ongoing motion patterns.
It really makes you wonder then, why wasn't this question, why doesn't a better telescope show a younger version, asked more forcefully before?
Well, motion theory suggests an answer for that too. It argues that the entire way we've built modern astronomy—
the telescopes, the detectors, the computer models—
exactly, the analysis techniques, everything. It's all founded on the fundamental assumption that light is photons traveling through space over time.
So that assumption is baked into the system at every level.
Deeply baked in. And because it was the unquestioned foundation, the question itself, why isn't there consistent temporal regression with better instruments, might have seemed irrelevant, or maybe just an anomaly to be explained away later within the existing framework.
It wasn't the question the paradigm was set up to ask.
Precisely. Failing to critically examine that basic observational fact allowed what motion theory calls the illusion of look-back time to persist.
Okay, this is fascinating. So, stepping back, if motion theory is onto something here, what does it tell us about the universe? What are the big implications?
They're pretty huge. First, obviously, light doesn't travel in the conventional sense. Detection is about resolving these motion rhythms locally.
Right.
Second, cosmic distance might not equate directly to look-back time. It might be more related to a loss of rhythmic compatibility or clarity of the motion pattern over vast scales.
Rhythmic compatibility, that's a totally different way to think about why things get fainter and fuzzier with distance.
It is. And it follows that better telescopes aren't peering further into the past. They're achieving a deeper, more accurate resolution of the present state of cosmic motion structures.
Deeper into the present, not the past.
Yes. And finally, it implies the universe might not be this collection of vastly time-delayed snapshots. It could be much more interconnected and, in a sense, in phase or contemporaneous than we currently believe.
Wow. Okay, so let's try to boil this down for everyone listening. The core argument spurred by this JWST data is essentially, if a better telescope just shows you the same thing but clearer, That strongly suggests you're resolving something that is currently real, right here, right now, not seeing its ancient history.
That's the crux of it. The consistent failure to see systematically younger versions of galaxies with JWST, despite its power, is presented as evidence against look-back time, and for this idea of real-time detection of structured motion.
So JWST's findings, ironically, might not be confirming light travel over cosmic time, but actually supporting this alternative view.
From the perspective of motion theory, yes. They see it as powerful, albeit overlooked, supporting evidence.
It's genuinely a provocative thought that this data from our most advanced telescope might be hinting at a massive shift in understanding reality itself. That look-back time, this concept so central to how we imagine the cosmos, could be an illusion.
And that the universe might be far more present and interconnected than we ever thought.
It definitely gives us a lot to think about. Thank you for walking us through that on this deep dive.